SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering basic and applied, and today we shall discuss about the impulse steam turbine. If we try to recall, in the last class we have talked about the classification of steam turbines, and we had seen that steam turbines or steam turbine can be classified into two different categories. One type is impulse type, another type is the reaction type. We have also studied about turbines in the context of fluid machinery or fluid mechanics course, and you have seen that the hydraulic turbines also can be classified into impulse and reaction types. So, we have discussed that for the impulse steam turbine, the name itself suggests that impulsive effect is responsible for the spinning or whirling action of the turbine wheel. What is that? So, impulsive effect is nothing but the difference in momentum of jets which is deflected by the blades. So, and that is described by Newton's second law of motion. So, we had seen that this particular type of turbine works on the basis that high velocity jets of water from a flow nozzle is directed onto the vanes or blades, and when the jets is flowing through the passage between blades, the jets get deflected and there is a change in or loss of momentum. So, the resultant impulsive effect, that is what I was discussing, that due to change in momentum the resultant impulsive effect spins or rotates the turbine wheel, and we are getting torque and we are getting output in the form of work. So, let me tell you, turbines are basically work interacting devices, and we are getting energy output in the form of work, but to get that work we also need to supply certain amount of energy. So, basically the amount of work that we are getting at the shaft of the turbine, that is at the cost of some input energy. So, the input energy is basically the kinetic energy of jets when jets of water strike the turbine blades. So, that energy is getting converted into the another form and we are getting work output. So, objective should be to estimate what fraction of that input energy is getting converted into the output energy, of course in the form of work, and if we can quantify that, we can estimate the efficiency, and that is very important. You have studied many subjects, many other subjects, and we have seen that any mechanical component, mechanical device, when it is designed, several aspects are considered for the design of that particular device, and one of the most important aspects is the efficiency. So, again while a designer is designing an impulse turbine, he or she must be careful about the efficiency. So, that means we need to know what is the amount of work that we are getting at the shaft of the turbine, and that work output we are getting at the cost of some input energy. So, to do that analysis we need to know little more about the impulse turbine, and that is what the topic of our today's class. So, let me tell you once again that before we go to discuss about that analysis, let us first draw the schematic depiction of this particular type of turbine, and from there we shall try to draw the velocity triangles, because without knowing the velocity components, rather the working principle in a more deeper way, it won't be possible to understand about this energy transfer process. So, it is convenient to draw, it is convenient to establish that particular energy transfer mechanism, or in the form of mathematical expression, if we can draw the velocity triangles. So, first let us draw the schematic of the impulse turbine. So, if we draw, and so this is the first row of moving blades or blades, and this is the first row of nozzle or fixed blades. So, though we have drawn here only one nozzle and two blades, because we need to know the passage between two consecutive blades. We are interested in analyzing the working principle in a more deeper way, and that too we are interested in to know about the velocity components. So, these two rows constitute together to form a stage, and that is the first stage, say. So, these two rows constitute together to form this stage, and what we know, that say this is the velocity of steam which is entering into the nozzle. So, steam which is coming out from the turbine now is entering into the flow nozzle, and as I said that steam turbine is basically assemblage of the row of fixed blades and row of moving blades or blades. So, that steam which is entering into the first row of moving fixed blades or nozzles, and that steam is essentially coming out with a higher velocity, and that is how the nozzle is or nozzles are designed, and that velocity is, say, this is C1. So, that C1 is the exit velocity, C naught is the velocity of steam entering into the nozzle, C1 is stream velocity at the nozzle exit. Okay. And the nozzle which is striking the blade or blades at an angle, say this is alpha. So, this angle is flow angle or alpha. So, this alpha is the flow angle. And after striking, as we have discussed that after striking the turbine blades at a velocity c1 with and that steam will come out from the blades say at a velocity c2. So, c0, c1, c2 these are the velocity absolute velocities. So, these are the vector quantities, but I am not going to write over for the ease in the representation, rather for the sake of the convenience in the representation. Now, c2 that is the steam velocity at the blade exit. Okay. So, now we shall be drawing the velocity triangles, but before we go to draw the velocity triangles, let us now look at the kind of this blading arrangements in a more clearer way. It is not like this. So, I can draw it, okay, and so if I now hatch these two blades, okay, and so this is the right, and this is the mean diameter dm. Okay. So, we have drawn two consecutive blades, and we can see that the steam which is coming from the flow nozzle, say this is the flow nozzle, and steam is entering with a velocity c1, say this is c0, and steam is eventually coming out from the blades with a velocity C2, right, and this we can understand the two diameters. So, this is d t and this is d r. So, this is basically root and this is tip, and you know that tip diameter and root diameter, these two diameters are not same. So, to calculate the velocity of the blade, we have marked here mean diameter and the blade speed Vb is calculated pi dm n by 60, where n is the RPM, and this is basically blade height. So, this is Hb. So, Hb equal to blade height. So, what we can see? We can see this is the typical arrangement, of blades which are mounted on the wheel of the turbine. This is flow nozzle. So, this is nozzle. So, steam is entering into the flow nozzle with a velocity C naught, steam is coming out from the flow nozzle with velocity C1, and that is definitely higher than C naught, and that is the inlet velocity of steam, the velocity of steam at the inlet of the blades, and after doing certain amount of work, steam is coming out with a velocity C2 from the blades. So, now we have seen here, this is the arrangement, and when steam jets striking the turbine blades at an angle alpha, that is the flow angle. So, now with this understanding, if we try to draw the velocity triangles, and these velocity triangles are very important to know the energy transfer process or mechanism. So, let us briefly discuss about the velocity triangles, and to do that, if we say consider a single blade, and say this is the Vb, and Vb is same. So, this is Vb, this is the nozzle. So, this is the absolute velocity of steam leaving the flow nozzle and entering into the blade passage, that is C1. The blades are rotating with a that is what we had seen in the last slide, that this wheel is rotating. So, naturally blades are rotating at a speed which is n RPM. Okay. So, blades are rotating what we can see from this schematic. So, since blades are rotating relative to the blade velocity, we can have, rather we shall have the relative velocity, and that is W1, and this is the flow angle alpha 1. So, the suffix 1 is used to denote quantities at the inlet of the blades. Similarly, this is C2, that is the absolute velocity of steam leaving the blades, and since blades are rotating, so relative to the blade velocity, this would be the absolute velocity and we can draw the velocity triangles. So, blades or this particular blade is rotating with n rpm. So, what we can see that this blade speed corresponding to n rpm can be written pi dm n by 60. So, we have calculated based on the mean diameter, and that is why I had mentioned the need of this particular mean diameter. So, the blade speed is same. Since the blade speed is same, we can superimpose this inlet velocity triangle and outlet velocity triangle on a common Vb, that is the blade speed. And if we do this, so I am writing we can do that because Vb is same. So, if we try to draw the common velocity, rather if we try to superimpose these two velocity triangles on a common Vb. So, this is Vb, this is C2 and this is W2, sorry, this is C1 and this is W1, sorry. This is C1, this is W1 and this is Vb, and this angle is alpha 1, right. Now, we shall superimpose the outlet velocity triangle here, so this is C2, this is W2, right. So, you know that we have drawn. Now, this angle is beta 2, that is the blade angle at the exit, and if we draw here, so this angle is beta 2 and this angle is beta 1. So, this angle is beta 1. So, beta 1 and beta 2 are the blade angles at the inlet and exit of the blades, right. Now, from this superimpose velocity triangles, next our objective should be to know about the rate of work done by the jets on the blades. So, basically you know that steam which is coming out from the flow nozzle with a velocity C1. So, if we know the mass flow rate of steam, we can calculate what is the kinetic energy of steam jets leaving the nozzle and striking the turbine blades. At the cost of that input energy, our next objective should be to quantify the output energy in the form of work, because essentially we are getting we are getting work output at the shaft of the turbine. Now, to estimate that quantity, this superimposed velocity triangles are very important. So, what we can understand that you have seen that. So, basically this is known as C theta 1 and this component is known as C theta 2. C theta 2 and C theta 2, C theta 1 and C theta 2, these two are the velocity components in the tangential direction. So, component of absolute velocity in the tangential direction is C theta 1, component of exit absolute velocity in the tangential direction is C theta 2. So, if we consider absolute velocity at the inlet, the component of that absolute velocity in the tangential direction is C theta 1. Similarly, component of absolute exit velocity is C2, I mean C2 is the absolute exit velocity, component of that velocity in the tangential direction is C theta 2. Now, this delta C theta equal to C theta 1 minus C theta 2. So, the change in or the difference in tangential component of absolute velocity is responsible to produce tangential thrust, and that thrust would give rise to the torque and we will be getting work. So, this quantity is very important to estimate the work done by the jets on the blades. Similarly, if you look at carefully, we still can have this particular component, and that is delta C A, that is C A 1 minus C A 2. What is C A 2? This is C A 2 and this is C A 1. Similar to what we could define wall component, that is C theta 1 and C theta 2. So, let me write C theta 1 and C theta 2, these are known as swirl component of velocity. In some books, these velocities are also known as swirl component. So, change in swirl component of velocity is responsible to produce tangential thrust. Similarly, the CA1 and CA2, these two are the component of absolute velocity in the axial direction, right. So, component of in the axial direction, and you can see that CA1 is not equal to CA2. So, the difference in the component of absolute velocity in the axial direction, that is delta CA, that is still there, and that component produces axial thrust. To observe what we can see, I mean you also can draw it to observe the I mean we can draw the velocity triangles, and by drawing velocity triangles we can see what would be the magnitude of this component delta Ca. So, this difference in axial component, I mean component of absolute velocity in axial direction can be observed if we draw the velocity triangles properly at per scale. What I would like to tell you, this particular component is there, and that component is responsible for the axial thrust that would be absorbed by the axial thrust bearing. So, basically the turbine should be mounted, the turbine that wheel is mounted on a shaft, and when it is mounted on a shaft, that axial thrust bearing should be there to absorb this axial thrust, whereas this delta C theta, that is solved component. So, the difference of solved component is responsible to produce tangential thrust. So, let me tell you two important angles here, because that would be useful to so, if we try to draw the angles in a clockwise, then this angle is gamma, that is the exit blade angle, that is nothing but 180 minus beta. So, if we try to draw the velocity, if we try to draw the angles in the clockwise direction, gamma is the exit velocity, exit blade angle, and that is nothing but 180 minus beta 2. Similarly, we can also have another angle if we try to measure the angles in the clockwise direction, and that is this angle delta. So, delta is the angle made by the exit absolute velocity of steam leaving the blades with the plane of rotation of the wheel, while this alpha, that is the flow angle, that is the angle subtended by the nozzle axis in the direction of rotation of the wheel. So, these two are important. So, let me tell you, this gamma equal to 180 degree minus beta 2, and this delta is the angle made by the exit absolute velocity of steam leaving the blades with the plane of rotation of the wheel. So, with this understanding, that means we could identify three different velocity components: absolute velocity. So, let me write here, C is the absolute velocity of steam, W is the relative velocity of steam, and Vb is the blade velocity. The absolute velocity would be there because steam will come out from the flow nozzle with an absolute velocity C1, but still the turbine blades are always rotating. So, relative to the blade velocity, steam which would be impinging on the blade, that is the absolute velocity with an absolute with a relative velocity W1. Now, with this understanding, what I said is that tangential thrust that is Pt. So, that is due to the change or difference in solved component of velocity, right. Now, if we try to look at the inlet velocity triangle, so let me write here from inlet velocity triangle what we can write? It is very important you know that inlet velocity triangle. So, this delta c theta equal to c theta 1 minus c theta 2, right. From inlet velocity triangle we can write, that is, let me draw the inlet velocity triangle once again. This angle is beta 1, this angle is alpha 1, and this is CA1, this is W1, this is C1, this is VB. So, we can write you know that C1 cos alpha 1 minus VB equal to W1 cos beta 1, right, we can clearly write. So, this component is W1 cos beta 1, right. So, we can write this. We also can write you know, we also can write C1 sin alpha 1 equal to W1 sin beta 1, we can write, right. So, from this we can write that tan beta 1 equal to C1 sin alpha 1 by C1 cos alpha 1 minus VB. It is very important. Okay. This C theta 1 and C theta 2, so you can understand that C theta 1 is basically component of absolute velocity in the tangential direction, that is nothing but C1 cos alpha 1. So, this is C1 cos alpha 1, and if we try to draw is the outlet velocity triangles. So, if we try to draw the outlet velocity triangles, right. So, we can draw it. This is VB, right. This is C2, this is W2, and this angle is beta 2, and this angle is delta. That is what we could define. Delta is the angle made by exit absolute velocity of steam leaving the blades with the plane of rotation of the wheel, and this angle is beta 2. So, we have drawn this is the beta 2, that is the blade angle. Of course, if we can draw the angles in the clockwise direction, then gamma would be the blade angle, exit blade angle. So, 180 minus beta 2. So, what we can write here that this is the outlet velocity triangle. What we can write? We can write that C2, so this is Vv and this is C theta 2. So, C 2 cos 180 minus delta plus Vb equal to W 2 cos W 2 cos beta 2, W 2 cos beta 2. That means, we can write Vb minus C 2 cos delta equal to W 2 cos beta 2. If we are expressing the, if we are measuring the angles in the clockwise direction, then it would be Vb minus C 2 cos delta equal to W 2 cos 180 minus, if we see 180 minus gamma, because beta 2 is equal to 180 minus gamma, therefore, minus W 2 cos gamma. So, just I am trying to write the expressions that we can get from the velocity triangles, because these expressions will help us to estimate about several other quantities. Now, what is C theta 2? C theta 2 is equal to C 2 cos 180 minus delta, that is minus C 2 cos delta. So, that is C 1 cos alpha 1 minus C 2 cos delta. So, I can write now, I can complete it this. So, this is now coming C 2 cos 180 minus delta. So, that means it is coming C 1 cos alpha 1 minus C 2 cos delta. So, this is the delta C theta 2. And what about axial thrust? This axial thrust that we had written over here, if we go to the next slide. So, you know that C 1 cos alpha 1 minus C 2 cos delta, C 1 cos alpha 1 and C 2 cos delta 2. So, C 2 cos delta we can have from this, also we can have C 1 cos alpha 1 from this expression. So, you know that C 1 cos alpha 1 minus V is equal to W 1 cos beta 1, from there we can calculate what is C cos alpha 1, C 1 cos alpha 1. Similarly, C 2 cos delta that we are getting from this expression. So, knowing these two expressions, we can quantify what would be the change in solved component of velocity, and that particular component is responsible for the tangential thrust. So, this tangential thrust, if we try to write, Pt equal to ms into delta c theta. So, this ms is mass flow rate of steam. If it is mass flow rate, then it should be m dot s, but it is mass flow of steam. Similarly, we can have axial thrust Pa, that is ms into delta Ca. So, we can quantify these two quantities, while the tangential thrust is responsible for the work output, that it will produce torque, we will be getting work output. The axial thrust should be also important equally, while someone is designing the impulse turbine, because this thrust should be absorbed by the axial thrust bearing. Okay. So, now if we try to quantify what is Pt, so you can understand, to estimate the work output from this particular energy transfer process, this Pt is important and Pa is also important, but this, since this component is not giving any work or any energy output, rather this component is important because the axial thrust bearing should be designed accordingly, so that this axial thrust can be absorbed. Otherwise, it will this particular thrust will lead to several mechanical issues, operational issues. So, Pt equal to ms into delta c theta, and this is ms into, we had seen that C1 cos alpha 1 minus C2 cos delta, right, that is what we have expressed. Now, see this C1 cos alpha 1 minus C2 cos delta. So, if we go to the previous slide, we can write C1 cos alpha 1 is equal to W1 cos beta minus plus Vb, while C2 cos delta is equal to Vb plus W2 cos beta. So, this is one way of calculating this expression. Also, we can write this Pt equal to ms into delta c theta, and this is ms into, just if we try to look at, you know, that if we go to the previous slide wherein we have superimposed these two velocity triangles. So, basically you know that W2 cos beta 2 plus W1 cos beta 1 is equal to delta c theta. If we try to look at this, you know, superimposed velocities, what we can see that this total, I mean this is nothing but W2 cos beta 2 plus W1 cos beta 1, right. So, as if W2 cos beta 2, this plus W1 cos beta 1 would be equal to delta c theta. So, if we try to write here, that is also equal to W1 cos beta 1 plus W2 cos beta 2. Now, while you know impulse turbines are designed in most of the cases wherein blades are symmetrical. So, that means beta 1 equal to beta 2. So, blades are symmetrical in most of the impulse turbine. That implies beta 1 equal to beta 2. If that is the case, we can write this is ms into W1 cos beta 1 plus W2 cos beta 1, right. See, let me tell you, you know that if we go here, when stream is entering into the blade passage and leaving the blade passage, this W2 and W1, these two, you know, relative velocities are not same. Though we are calculating the blade speed with the, you know, average or mean diameter, based on the mean diameter, these two relative velocities are not same, and it is due to the friction that the steam jet will encounter while passing through the passage between two blades. That also depends on the roughness of the blade. So, the roughness of the blade surface, that will provide a resistance to the flow of stream while passing through the passage between two blades, and it is because of this reason, you know, W1 is not equal to W2. So, W2 is always less than W1, and the ratio of these two you know relative velocities. So, relative velocity of steam, you know, the ratio of relative velocity of steam at exit to that at inlet is known as blade friction coefficient. So, we can define that blade friction coefficient that is equal to Kb equal to W2 by W1. So, what is this? So, this is the ratio of relative velocity of steam at exit to that at inlet. Okay. And we have seen that these two velocities are not equal, because steam while passing through the passage between two consecutive blades will have will face resistance, and that will come from the frictional effect. So, that is roughness of the blade surface. So, Kb is not equal to 1. So, we can write from this expression that W2 equal to Kb into W1, right. So, we can write this quantity again. So, we can write this Pt equal to Ms into W1 cos beta 1 plus K into Kb into W1 cos beta 1. So, what we can do? We can take Ms into W1 into cos beta 1 into 1 plus Kb. So, W1 into cos beta 1 we are taking outside the bracket, and we can write this, and W1 cos beta 1, this quantity can be written, that is what we have already established this expression. So, W1 cos beta 1 is nothing but C1 cos alpha 1 minus Vb from the inlet velocity triangle. So, if we write here, so that is nothing but Ms into C1 cos alpha 1 minus Vb into 1 plus Kb. So, this is from the inlet velocity triangle. Okay. So, try to understand, our objective is to express this tangential thrust in terms of blade velocity, flow angle, and also the blade friction coefficient. So, you know that since W2 is not equal to W1, there is always a loss of energy due to the friction of due to the friction while steam is passing through the blade passage, and that is nothing but W1 square minus W2 square by 2. So, that is known as loss of energy. So, the input energy, so when steam jets come out from the flow nozzle and striking the turbine blades, a part of that energy would be utilized to overcome the frictional losses, and that is due to the roughness, surface heterogeneity of the blades, roughness factor most importantly. So, if we go one step further, then we can write that Pt equal to Ms into C1 cos alpha 1 minus Vb into 1 plus Kb. So, this is the axial thrust, right. So, this is not axial, this is tangential thrust. Okay. So, what is work done? So, what is work done? That is work done by the jets on the blades. So, this is work done by the jets on the blades. I should write rate of work done by the jets on the blades. So, that is nothing but Pt into Vv, right, and so this is the work output. So, this is work output, and we can say this is the energy output in the form of work, right. So, that is output energy in the form of work. What about input energy? So, input energy equal to half Ms into C1 square, because this is the absolute velocity of steam leaving the flow nozzle and striking the turbine blade. So, if ms is the mass flow rate or mass flow of steam, then we can write this. So, from these two quantities we could express the work output, that is considering the energy transfer process, representing the velocity triangles both at inlet and outlet of the blades, and from this analysis we could write this is the work done Pt into Vb. So, that would be nothing but ms C1 cos alpha 1 minus Vb 1 plus Kb into Vb, right. So, this is the expression that we can write, and from there now what we can do, we can define. So, this is the work output or energy output in the form of work, and this is the energy input. Certainly these two quantities are not same, if they are same then efficiency would be 100%, and that is not possible because we all have studied about thermodynamics. So, this is not, I mean these two quantities are not same. In fact, that we also have studied in thermodynamics that work is high grade energy and energy heat is low grade energy. So, basically we are supplying heat to the boiler, and at the cost of that input energy you are getting this work output. So, suddenly work that we are going to get at the shaft of the turbine should not be equal to the input energy that we are supplying through the steam jets. So, we can estimate the efficiency, and that efficiency is known as blading efficiency or diagram efficiency. So, blading or diagram efficiency, this is called eta B, or if it is diagram efficiency eta B, eta D. That is nothing but the rate at which work is done by the jets on the blades. So, that is Pt into Vv, and that is the input energy, that is half ms C1 square. So, if we try to write this eta B or eta D equal to, we can write ms into C1 cos alpha 1 minus Vb into 1 plus Kb into Vb divided by half ms C1 square. So, we can write one step further, that means we are getting twice Vb into 1 plus Kb C1 cos alpha 1 minus Vb divided by C1 square. So, this is the expression that we can write, and if we go one step further, we can write this is, if we take out Vb outside and if we write twice Vb square by C1 square into C1 by Vb cos alpha 1 minus 1 into 1 plus Kb. So, this is what we can write. What we can see, that we can see the ratio of Vb by C1. So, we can write this is cos alpha divided by Vb by C1. So, we can write a ratio of Vb by C1, and that is known as velocity ratio Vr. So, this Vb by C1 is known as velocity ratio and Vr. So, we can write this is Vr. Okay. So, if we express Vb by C1 as Vr, then we can write eta D or eta B like this, eta B or eta D, that is twice into Vr square into cos alpha 1 by Vr minus 1 into 1 plus Kb, right. So, we can write that is 2 into Vr cos alpha 1 minus Vr square minus Vr square into 1 plus Kb, right. So, what we can see that we could write this is the diagram efficiency or bleeding efficiency, that this expression gives us an estimate about the energy transfer. So, what fraction of the input energy is going to converted in the form of useful work, that means we are getting at the shaft. I can't say that is useful work, because the work which is available at the shaft may not be available in real applications, because there will be several other losses like frictional losses, bearing losses, etc., etc. But at least we can see from this expression that what would be the fraction of what fraction of input energy would be converted into the work. Now, what we can see that this bleeding efficiency or diagram efficiency is a function of flow angle, blade friction coefficient, and most importantly the velocity ratio. So, there must be an optimum value of here for which this diagram efficiency or bleeding efficiency should be maximum. So, alpha A1 is fixed because it depends on the designer. Kb basically blade friction coefficient, because it cannot be equal to 1, but ideal situation would be that if we can maintain somehow Kb equal to 1, but at least this Vr, that is Vb by C1. So, basically why C1 is important, because the nozzle steam jet which is coming out from the flow nozzle and striking the turbine blades. So, there would be certain amount of loss of energy. So, that means what would be the optimum speed, optimum velocity ratio for which this efficiency should be maximum. If we do this, that is d eta b by dVr equal to 0, right. If we make it, I can write it, because it is function of Vr as well as alpha and Kb. So, I can write like this, delta Vr equal to 0, then we will be getting Vr will be equal to optimum, Vr will be equal to Vr optimum, and that is cos alpha by 2, cos alpha 1 by 2. And if we plug in the optimum value of Vr into the expression of eta d, then we can write eta d max or eta b max equal to 1 plus Kb into cos square alpha 1, cos square alpha 1. So, what we can see that we could establish the expression of bleeding efficiency or diagram efficiency, and we had seen that the bleeding efficiency or diagram efficiency is function of speed, velocity ratio, flow angle, and also the blade friction coefficient. Just to obtain what would be the optimum velocity ratio for which the efficiency should be maximum, and we had seen that the optimum value of velocity ratio is cos alpha 1 by 2, and plugging in the value of this Vr in this expression, we had obtained that this is the maximum efficiency or maximum diagram efficiency or maximum bleeding efficiency, and that is nothing but 1 plus Kb into cos square alpha 1. So, what we can conclude from here is that that if we reduce alpha 1, then efficiency should be maximum. So, if we can reduce the flow angle at the inlet, then efficiency or bleeding efficiency or diagram efficiency can be maximized. But if we reduce the flow angle drastically, there will be certain amount of loss of energy, and that and to maintain a balance between the loss of energy and maximum efficiency, this typical value of alpha 1 is 16 degree to 22 degree. So, if we can write that if alpha is less or alpha is small, alpha is smaller, eta d will be higher. So, this is what we can see from this exercise, but we cannot go beyond this value, because otherwise instead of having maximum efficiency there will be a loss of energy even at the inlet of the blades, and that is why this the value of flow angle is maintained within this in this range. Okay, to summarize today's class, we have discussed about the energy transfer process inside the impulse turbine, and from there we could explain the velocity triangles. Mapping the velocity triangles on a common VB, we have tried to estimate about the tangential thrust which is responsible for the work output, and finally we could express the blading efficiency or diagram efficiency, and we had seen that this particular efficiency is function of several parameters, and from there, from that particular expression we had established the optimum velocity ratio leading to maximum diagram or blading efficiency, and finally we had seen that the recommended value of alpha for which efficiency will be maximum without inviting extra loss of energy at the inlet of the blades. So, with this I stop here today.